proof of the theorem of the theorem 1.5.4 it is technical, and we will prove it in 3 steps. And in the first step, our aim is going to see that, like in the Riemann row spaces, if you consider the 2 divisors A and B is less than or equal to B with respect to partial order on the divisor group, then the Adel spaces of A is a subspace of the Adel space of B, and similarly in the quotient of the Riemann row space, the quotient of these Adel spaces has dimension exactly degree B minus degree A. And like in the proof of the lemma 1.4.8, first we suppose that B is in the form of A plus B or for some place P. By choosing a uniformizer or the prime element for this fixed place P, let me denote by T, we can write VP of B as the VP of A plus 1, and let me denote VP of evaluation of this divisor or the component, the coefficient at the P component by N. We can introduce a map which sends the Adels in A of B to evaluation of its P component, a multiplication by its P component by T to the N, and its evaluation at P. Indeed, again, we can see that this definition, the definition of phi, makes sense in the sense that if we look at the evaluation T to the N alpha P, because we want to see that this T to the N alpha P is element in OP, so that means it doesn't have pole at P, so that means its image cannot be infinity. In order to see that, we check the evaluation of this function, and by the properties of the discrete evaluation map, and since T is the prime element of P, and alpha is an Adel in the Adel space of the divisor P, so that means VP of alpha P is bigger than or equal to VP of B minus VP of P for all places P. Indeed, we can see that it has always positive valuations. So the image is not going to be infinity, and this definition makes sense. And we can again see that phi is k-linear. So that means phi of A alpha B beta, if you consider component-wise scalar product and addition, this is going to be A times phi of alpha, B times phi of beta for the Adels alpha and beta, and the scalars A and B. But differently from k-linear map we consider in the proof of lemma 1.4.8, in this case we will see that this phi is is in this surjective, and this surjectivity can be obtained the rich structure of this other space of the divisor B. Indeed, in order to see that, our claim is that if we consider a function Z from OP, so that means if we consider a function in the residue class field, we want to see the existence of the adile, which lies in the adile space of the divisor B, such that its image is going to be the evaluation of the function Z at P. And in order to see this, the existence of such a adile, my claim is that if we introduce a sequence whose pth component for the P which appears in this equation can be introduced as a function as t to the minus n times z, and at other components we will consider the functions which is defined in terms of the uniformizer of these places. But more explicitly, since we want to see that this adile is an adile space of the divisor, particularly we consider these functions as the VQB minus VQB powers of the uniformizer of the place Q. Let me check briefly. This is an adile in the adile space of the divisor B. This is true because for place P, for the pth component, we know that its valuation is going to be bigger than or equal to minus b, because VP of Z is positive since we consider Z from OP, and VP of T is 1 because T is the prime element for the place P, and indeed this is always bigger than or equal to minus VP of B. And for the other places which are different from P, if we consider the evaluation of the function at the qt components, by our setting, we can also see that this inequality holds for the other places Q. And this is also adile, so that means we have VP of alpha P negative for finite many places. Please check, and probably we will talk about in the discussion session. And indeed, this surjectivity gives us allows us to compute this dimension explicitly as degree B minus degree A, because the kernel phi is going to be the adile space of the divisor A, because the kernel of this K-linear map contains the adults from the adult space of our domain, and their images are the zero of the residue class field. And here still T denotes the prime element of the place P. So that means these are the adults such that T to the n multiple of their Pth component is strictly positive valuations at P, or these valuations are bigger than or equal to 1. And please note that we are still in the setting for A and B, and A and B are in this form. So that means VP of B is VP of A plus 1, and we fix VP of B as M. This is going to be the same M. And we can write 1 as N minus VP of A in this case. And this shows us VP of alpha P is bigger than or equal to VP of A. And indeed, this gives us an adile. If we, so this tells us if we consider an adile of the adile space of the divisor, this lies in this set, but particularly for the setting, you can also see that this kernel phi is also lies in A of A. And like in the proof of the lemma 1.4.8, again by first isomorphism theorem, we can conclude that in this case, this quotient space is going to be isomorphic, the residue class field. That means its dimension indeed is going to be degree of P, and the general case is follows from the induction over the number of the P's which appears in this equation.